we are going to do a quick review of chapter 1, and we're starting with interval notation. So if we were to look at this interval notation, one of the easiest things to help us would be to do a quick sketch of a number line. So if I just did a real quick sketch and I put on some numbers here like -20, -10, 0, 10, and 20, I would throw in this -17 and it would be a closed circle, and it would go to 12 and then it would stop to a closed circle. So this is what this bottom interval would look like. And then we start again at 16 and then we go to infinity. So this is what it would look like on a number line, and we want to take that number line and we want to transfer it into interval notation. Now interval notation always goes from low to high. All right, and then in interval notation we're using parentheses or brackets. So because this is equal to -17, we would have a bracket here. The low is -17, the high is 12, and another bracket. So we're including the -17, we're including the 12, they're both equal, just like the closed circles. So this is the bottom interval, and then it jumps. So the symbol for that is a U for union. Some will also accept the word or. And then the low on this interval is 16 and the high is infinity. And in both we would include parentheses because it does not include the 16, and infinity can never be equal. We never reach that. All right, number 2 asks us to simplify something that is in roots. So the first thing I want to do is look and see if I can reduce my roots. If they do not reduce as a fraction, the next thing I want to do is if I can break any of these numbers down and get a perfect square out. That doesn't work, so now I'm going to jump into rationalizing my denominator by multiplying it by itself. And so I'm really multiplying by 1. So when I go to do this, my final cleaned up denominator is 6. That comes from the square root of 6 times 6 is the square root of 36. The square root of 36 is simply 6. In the top, we're going to put this together. We're using that idea that the square root of a times the square root of b is equal to the square root of ab. So this would be 5, and it'd be the square root of 42. Now before you walk away from one of these problems and think that it's done, you want to make sure that you're looking to see what else I can do. Can I reduce my fraction? Can I break down the root that I put together? There are no perfect square factors in 42, so that is your final answer. All right, in this next problem, you are simplifying by adding or subtracting. So I can only add or subtract if I have common terms, and they have to be the exact same thing underneath the root sign. So I would keep the 5 square root of 6x because the 6 doesn't break down. The x would stay because it's not a perfect square. And then I bring down my minus sign, and I want to break down the 24. And so the numbers I'm interested in are perfect squares, like 4. So 4 times, keep that 6 with the x because I cannot break it down further. Even though 2 times 12 works, they're not perfect squares. So we get 2 square root of 6x. And with that in mind, now they're like terms. So I have 5 of these minus 2 of these, and I get 3 square root of 6x. And that is my final answer. All right, and number 4, we're asked to evaluate. So we're using our roots. And so if we look at this, I have 5 to the -3. Well, negative exponent is the rule to move it to the bottom. So we're taking the reciprocal there, or inverting it. So this would be 1 over 5 to the positive third, which simplifies to 1 over 125. All right, and number 5, it's a little more involved. We have some variables here. And in order to simplify this, I want to follow the order of operations. So in here, before I distribute my power of 3, I want to clean this up. A -2 is simply a -2. It doesn't move, it's a negative number. This x to the -4 is going to come down using our rule for negative exponents. It's the only thing that's moving. The y is positive exponent, the x is a positive exponent. So I end up with a fraction, all the power of 3. I keep the -2, I keep the y to the 7th, but when I take this -4 and I shift it down, it becomes x to the positive 4. So I had 5 of these, I put another 4 there, so down here I have x to the 9th. Now, the rule for a power to power is that I multiply. So when I have a to the m to the power of n, I multiply a to the m times n. So don't forget your -2 goes to the third. So that'd be 3 negative signs, so I get -8. A power to power we multiply, so y to the 21. And again, we multiply, so x to the 27. Make sure you have no negative exponents. Any number should be cleaned up and reduced, and variables should only show up one time. In scientific notation, we always want our number to be a digit between 1 and 9, a decimal place, nearest hundredth times 10 to a power. So be careful with adjusting. So there's two ways of doing this. I can type all of this into a calculator, but you would need to use parentheses, divided by, and then follow with parentheses to get it done correctly. If I do it in parts, and I take 2 divided by the 8, I get 1/4 or 0.25 times 10, because remember, we keep the base and we subtract. So that'd be 10 to the -7 minus a -9. So I'd have 10 to the +2. If you look at that and you see scientific notation, because 10 to the second, you have to double check your front number. It should always be a number out front between 1 and 9. So in this problem, we have to adjust it to be 2.5 times 10. And remember, we want to see what it takes to go back. So you put the decimal here. To go back, you go 1 to the left. And so if I had a power of 2, I adjust it 1 to the left, I now have a power of 1. Now, if you type this whole thing in the calculator, that's my answer, I'm done. If you type this whole thing in the calculator, you're going to get out the number 25. That's what your calculator gives you, but it's not in scientific notation. So again, you would adjust it to make it 2.5 times 10, but what would your power be? Your decimal was there. You put the decimal here, so to go back, you go 1 to the right. So that is where we get that power of 1. So we get the same outcome either way. Okay, in the next problem, if we do this in parts, we multiply our numbers 3.2 times 5.0, and we get 16 times 10, and when we multiply the bases, we add, so it'd be times 10 to the -5th. Again, that is not scientific notation, so we need to adjust it to make it 1.6 or 1.60 times 10 to the what? And again, it's what it takes to go back. So we put the decimal here. To go back, you need to go 1 to the right. So if I had -5 and I adjust it +1, I now have a power of -4. So there is your scientific notation. Now, if you type all of this in the calculator at once, your calculator gives you the decimal 0.00016. That is not scientific notation, so again, the first significant figure we hit is 1.6 times 10, and again, we put the decimal here. So to go back, we go 1, 2, 3, 4 to the left, and that is why my power is -4. So we'll get the same outcome either way. We have adjustments to make. All right. On number 8, this is about the order of operations and your negative signs. So when I go to do this, I'm going to replace every variable exactly where it is with parentheses. So here I go. I have 5 times y, which is -2, minus 2 times x, which is -4, minus x squared, which is -4. So the biggest mistake that I see is canceling these two negative signs. If this power was not there, absolutely negative times a negative makes a positive. But with that power there, following the order of operations, we have to deal with the power first. So there's no parentheses to deal with. It's only multiplication and exponents. So first thing I'm going to do is my exponent. So bring all of this down. Bring my minus sign down. I have to address the power before I can multiply. And a negative times a negative is multiplication. So power first, so minus 16. Now I can go through and do my multiplication. There's -10. That's going to be a positive 8. And then there's my minus 16. I put it together. I get -2 minus 16. I get a final answer of -18. In number 9, we want to determine if this relation is a function. So a relation has every x has a y. And a function, every x has exactly one y. So the quick check is, does the x value repeat itself? If x does not repeat, then there's no chance that this value of 3 has more than one answer. So this is a function, and it's a function because every x has exactly one y. Every x has exactly or only one y. That's really important that we look for that. Now, if I look at example or problem number 10 here, I'm asking if this one's a function. And so if you look at it, this is given to me as a table, not in roster notation. And I see that the x is 5 repeats itself. Now, if this was 5, 2 and this was 5, 2, it's still a function because x is 5 and only has one outcome. But because I have a 5, 2 and a 5, 4, it is not a function. The reason cannot be every x has more than one y, because it's only when x is 5 there's more than one y. So you can get specific. It's not a function when x equals 5 there's more than one y, or some x's have more than one y, something like that. So looking, does every x have exactly one y? Now in number 11 we have two graphs. In order to tell if a graph is a function, we can simply perform that vertical line test where we check and see if a vertical line passes through more than one point. So this one does not, so it is a function, and the reason we can say is that it passes the vertical line test, and we're going to go ahead and abbreviate that. This one fails the vertical line test. You can see that you hit 3 points on a vertical line. So this is not a function. It fails the vertical line test. Now, why does that connect to every x has exactly one y? If we estimate this to be x is negative 2, then when I have x is negative 2, I have a positive y value up here. Maybe it's 8 or 6. And I have a positive y value up here. And then I have another y value down here. So when x is negative 2, I have 3 different y values. So that breaks our rule. All right. In number 12, a couple things here. First of all, it says to give the domain and range. Is it a function, and explain. Okay, so is this a function? Yes. It passes the vertical line test. Every x has exactly one y. All right, so we've got that part, but let's talk about the domain and range of the given graph. The domain are the x values. So when I talk about domain, I want to know what x can be. And notice it says to give an interval notation. I could not do roster notation and list all these points, because between x being negative 3 and x being negative 2, there's infinite points here. So the domain, the low value of x, as I come scan across the x-axis, the low value is at negative 3. And it's a closed circle, so it's going to be a bracket and include it. And then as I go, it keeps on going. And so it goes to positive infinity, because my graph will keep extending. The range, that comes from the y values. So as I scan the lowest y value, I hit this right here at 1. And I know I see this coming to the right, but as it goes to the right, it also is going up slowly. So there's no limit to how high this gets, so the y value also goes to positive infinity. And again, we are going to include that. So I want to take a minute and extend this problem. I want to add to this problem a little bit, so I'm going to put another graph on here. I'm going to do that in blue. I'm going to make this an open circle on the 2, and it's going to run up, hit off of that, and then come on down. So that's the graph I'm making up. And in this graph, I want to talk about the domain and the range. So I wanted to extend this example a little bit. So when I look at this graph and I ask for the domain, as I come across from the negative side, because I always want low to high, my graph keeps pushing down negative infinity. So the low is negative infinity, so make sure you always go low to high. As I come across the graph, the last point I hit is x is at 2, and notice it's an open circle, so it would be a parenthesis. Now the range, again low to high, as my graph comes down this way, it is coming down the y-axis. So the low again is negative infinity, and a lot of people want to say that the high stops at 0. But doesn't this graph pop up? It hits the y value of 1 and then comes back down. So if you scan, that's the highest y value, and that is at 1, and it is included, so I put a bracket there. All right, last extension I want to do on this, I'm going to put some points on my graph. So maybe I have a point at 3, 1, and I have another point at 4, 0, and 5, 2, and we'll make it something like 6, negative 1. So my yellow graph, let's talk about the domain and the range. And the reason I want to do this is because I want to contrast that if I have just points, that creates a discrete graph. And in a discrete graph, I cannot use interval notation. I have to use roster. Okay? So I can't say that the x values go from 3 to 6. Because if I say that they go from 3 to 6, then I have to include the 3.1 and 3.5, and there's no points in between there. So when I'm looking at this, the domain in roster notation, the low would be 3, because I have a point at 3, 1, and I have a point at 4, 0, and I have a point at 5, 2, and a point at 6, negative 1. So those are the possible x values. And in roster notation, the y values would be at 1, 0, negative 1, and positive 2. So I'm going to go ahead and put those in order. And so I wanted to show you domain and range of a discrete graph must be in roster notation. Okay, now next idea, we are going to evaluate. So this takes us into function notation. Now first of all, I'm going to look at this and say it's not a function because it fails the vertical line test. So I know they don't ask that, but it's not a function, it fails the vertical line test. And so let's talk about what this means. We're evaluating for f of 0. So we need to remember that f of x is the same as y equals. And so we are putting in the x value of 0, and we are trying to find the y value. That's what we're trying to find. So if I know that x is 0, I'm going to go to my graph. Here's where x is 0. But anywhere I go vertically, x is always 0. So it's a horizontal line, and it hits the graph in 2 spots. So we actually have 2 outcomes. I'm going to estimate it to be 1.25 or positive 2. Those are the 2 y values I get when x is 0. So that's why it's not a function. One x value has more than one outcome for y. What is the function at negative 2? So when x is negative 2, what is the y value? So here's where x is negative 2, and it hits the graph right there at positive 2. When the graph is at the x value of 3, right here, and again right here. So find your x value and see where it would hit that vertically. This is the line x equals 3. And so we'd have values at 0 or at positive 2. Again, that's an example of why it's not a function. All right. In number 14, I'm going to go ahead and extend that problem also. So we have a mechanic charges $40 for a diagnostic test and then $35 per hour of labor. So we want to write a function to represent the total charge C for h hours of labor. All right, so I'm going to go ahead and put this in function notation. The total charge for h hours is, all right, so just like f of x, we start off with a $40 fee. So if we get this diagnostic test and they say there's nothing wrong with your car, I pay $40, I get my car back, I walk away. If we pay this diagnostic fee and we find that something is broken, I need new spark plugs, obviously you're going to pay for that, but you're also going to pay per each hour of labor. So on top of the diagnostic fee, I'm going to pay $35 for every hour the mechanic is working on my car. So 40 plus 35h. That is part A, that is my function. Now I'd like to extend this. Part B, find C of 5. Okay, so if I'm asking you to find C of 5, I'm asking you to put in an input of 5. So that would be C of 5 is equal to 40 plus 35 times 5. So we need to know what C of 5 equals. And I believe it's 215. Yes. So I just multiply, add on the 40, I get 215. So that is good. The answer is in function notation, but because this is a word problem, we would put our answers in words. So then I'm going to extend it one more time, and part C is going to say write meaning of part B in words. All right, so we're going to write the meaning of part B in words. So the input was 5, and that was the H value that stood for hours, and the output was the total charge. So what will we have? For 5 hours of labor, total cost is $215. All right. So in our parent functions, we see that we have a power of 2, and that makes the parent function a quadratic, and the parent function is y equals, or f of x equals x squared. We can also talk about this being a shift 5 to the right, and we can do that by graphing it using a t-chart or looking on a graphing calculator. All right, and the last problem comes from our first section of classifying. So before I classify anything, I want to simplify it. So I know that this is truly -9. So how does -9 classify? Well, it is a real number. It is rational because it can be written as a fraction or a terminating or repeating decimal. And it's also an integer. Integers are positive and negative whole numbers. The square root of 32, yes, I can break that down. Square root of 16, square root of 2, but it's the idea that I will always have a square root here. It's not a perfect square, so this is real, but it is irrational. It does not terminate, it does not repeat, and I cannot write it as a fraction. Square root of 25 simplifies to 5. So always simplify your numbers. Again, this is real. It is rational. The next subset would be integer. It falls into that category. It is also a whole number. So remember, whole numbers start at 0, then 1, 2, 3. Integers are positive and negative whole numbers. And it also classifies as a natural number. Natural numbers start at 1, then 2, then 3. So it's the only difference between whole and natural is the 0. The symbols, if you're using them, are a double-lined R, a double-lined Q, a double-lined Z, a double-lined W, and a double-lined N.